done detail we have done detail about the valence bond theory. So let us try to find out the limitations of valence bond theory. Okay, so see, valence bond theory, though it tells us about the magnetic, paramagnetic and diamagnetic nature of a complex, but it cannot give us the finer detail. Okay. It cannot explain the detailed magnetic properties of complex compound. It cannot explain the color of the complexes. In your book, they have actually mentioned about the optical properties. Optical properties is nothing but the color. So let us try to make it simple. It gives no information about the quantitative and thermodynamic stability of the coordination. Or it cannot predict properly. Whether a particular coordinated complex is a square planar or tetrahedral. In nature. 5. It fails to make distinction between strong and weak ligands.
Sir, done.
Good. Now we'll go for crystal field theory. Today I'll just give you a brief information. Then I'll explain to you on Thursday. It seems in army school is open and they are having practical started from today. Aparajita has gone. Let's see when your school. I think in that case next week I may start the class by 7:30 like previous routine. Crystal field. See, in valence bond theory, what did you find? In valence bond theory, please don't write now. In don't write. In valence bond, sorry. According to valence bond theory, the central metal atom or ion provided S, P, and D. Here we'll write inner or outer. orbitals to undergo hybridization. Then after that, what? The ligand provided a pair of electrons provided an orbital filled with pair of electrons to overlap empty hybridized orbitals of central metal atom or ion to form coordinate covalent bonds. Thus, between metal atom or ion and ligand are linked with each other to bonds. There is the summary of the valence bond theory. This, okay. Now, in case of crystal field theory, they said no, it is not like this. In case of crystal field theory, it is proposed that metals and the ligands do not form any bond at all. They only remain side by side, just like ionic compounds. Okay, they remain side by side. Huh? So in crystal, write only for understanding, don't write. In crystal, because I've already given you a note. In crystal theory, it is assumed that metal, atom or ion is surrounded by neutral or ionic ligands. Huh? In crystal field theory, it is assumed that atom or ion is surrounded by neutral or ionic ligands and are held with each other simply by electrostatic forces of attraction. So that is the main difference. It is held, they come nearer to each other and they are held at a fixed distance through electrostatic forces of attraction. That is the crystal field theory. And they have a specific direction or path by which the ligands come. Okay, so we find that d orbitals plays a very important role in the crystal field theory. So we know that petal has 5 d orbitals: dxy, dyz, dzx, dx square minus y square, and dz square. dxy, dyz, dzx are in the plane, and dx square minus y square and dz square are along the axis. So in that case, you'll find that some of the ligands may approach along the axis. So as the d orbital has having electron and the ligand is also having electron, so when they approach along the x, y, and z axis, then the dx square minus y square and dz square suffers severe repulsion because like charges repel. Ligand is also having electron and the metal d orbit is also having electron. Otherwise, as such, we know all the 5 d orbitals have the same energy. But when the ligand approaches, the repulsion takes place. So in that case, you will find the degeneracy. Degeneracy means having equal energy. The equal energy of the d orbitals gets disturbed, and due to repulsion, the energy of the orbitals along the axis, that is dx square minus y square and dz square, increases, and at the same time, the energies of the other 3 orbitals dxy, dyz, dzx decreases, and the 5d orbitals which were earlier like this having the same energy, then they split. You find this is dx square and dy square due to repulsion goes up, and dxy, dyz, and dzx goes down, and that leads to splitting. Okay, so in that case you will find, see, everything word by word, the simplest possible language I have explained to you in the note. So in that case, what happens? The due to splitting, the orbitals they separate from each other. Now, the magnitude of splitting does not depend upon the metal atom or ion. The magnitude of splitting depends upon the nature of the ligands. So those ligands which can donate electron very fast, that is, those are having labile electron, very fast electron they can give, in that case, the splitting is maximum. And those which are less, that is, those who are less electronegative, that creates more splitting. And those who are more electronegative, in that case, they hold a negative charge or electron charge with them. In that case, they induces less splitting. So on the basis of that, you will find the crystal field splitting differs. So those, with those cases where you find the splitting is maximum, those ligands we call strong field ligand, and those ligand which creates less splitting, we call them as the weak field ligand. So now, in due to this, you find the electron distribution changes. Okay, so please excuse me for today. I have to go have an important work. So Thursday, now you can write down all this thing. Thursday,